So you're going to define Bronsted-Lowry acid. You are going to define Bronsted-Lowry base. You are going to define Amphiprotic. You are going to define diprotic and triprotic. And then finally, you are going to name this ion. So you're either going to write them down or you're going to tell your neighbor, I don't care which. How are we doing? Are we ready? If you're unsure, make sure you've checked with the people around you, because I'm going to haul out my cards again. So if you don't know and your neighbors don't know, go find someone who does, because I'm going to call a random name. Give me a little wave when you're ready. Are you guys ready now? Are you guys ready? Are you guys ready? No, but you didn't talk to anybody. Oh, okay. Okay. Bronsted-Lowry acid. Sylvia. Yeah. Proton donor. What do we mean by proton? Hydrogen. Good. Bronsted-Lowry base. Rashika. Proton acceptor. What does it mean if a species is amphiprotic? Katie is not here. Jaden. Yeah, it is able, it's not that it has an acid and a base, it is that it is able to act as both an acid and a base. Did you guys like the picture of the frog for your homework? Amphi, meaning both. Amphibians can live on both land and water. This can act both as an acid and a base. Diprotic, Victoria. Can donate 2 H plus ions, yes. And therefore triprotic, Tiago, can donate 3 H plus ions. And let's name this ion H3O plus. Juan. Sorry. Never mind, go. Name this ion. Hydronium, excellent, okay. Did anyone have any questions from anything we did in the last, that you did like homework-wise in the last 2 days? Okay, I'm going to ask you another question. How can you recognize an amphiprotic species? How can you recognize an amphiprotic species? Have a chat about that. Once again, I will draw a card. So if you don't know, chit chat around until you find someone who does. Nobody had questions, and yet everyone's like, I don't know what an amphiprotic species is. Well, there's a on page 119, there was a question, which of the following would be expected to exhibit amphiprotic behavior? Did we not do that? I think we did. How can you recognize an amphiprotic species? Are we ready? No? Okay, so let's go back to our definition. It is able to act both as an acid and as a base. So what are the two things it needs to be able to do? It needs to be able to accept a proton and donate a proton. If it must be able to donate a proton, what can you say about the chemical species? It must have an easily removable proton. Okay? So that's one of the things. Must have an easily removable proton. Second thing, if it's going to accept a proton, so the second thing it has to do is it has to be able to accept a proton. What's going to make something more easily able to accept H plus? if it has a negative charge. Okay, therefore it must have a negative charge. Now, there are two exceptions to this. First exception has no negative charge. Anyone know what it is? Water. Yeah. The second one, it has an easily removable H, and it has a negative charge, but it is not amphiprotic. Yes. HPO4. Good guess. Not true. HPO4 is amphiprotic. HPO4 can give away a proton. Let's just put it with water. And become PO4 3 minus and H3O plus. Whoops. I forgot to do the H. H3O plus. And HPO4 2 minus can accept a proton from water and become H2 PO4 minus plus H3O plus. So HPO4 is amphiprotic. Let's go take a look on our data booklet, page 5. So we need something that has an H plus, has a positive charge, a negative charge, but is unable to act as a base. So let's look at our bases. Can you find, what's the first thing you come across that has an H and a negative? HSO4. So we have HSO4 here on the base side, and we have HSO4 here on the acid side. I would like you to look at the arrows. Is HSO4 amphiprotic? Can HSO4 donate a proton? Yes, there it goes. It is donating a proton. Can HSO4 accept a proton? What does a one-way arrow mean? H2SO4 is a, what kind of acid? Strong acid. And what do we know about strong acids? They dissociate completely. So, if I had some H2SO4, here is my H2SO4, and my proton comes off, will the proton go back on? No. Therefore, can HSO4 minus accept a proton? No. Okay? It is thermodynamically unfavorable. It will not happen. Okay? So HSO4 minus and all of the other bases, these guys here are the conjugate bases. Do you remember that term? Did you learn that term yesterday? Should have a little bit. Yeah? These guys are what we call the conjugate bases, and we'll talk about that more in a moment. They are the conjugate bases of strong acids. Now, what do I mean by a conjugate base? Well, if this is an acid, HA, let's just call this A, okay, for acid, when the hydrogen comes off, it becomes A minus, yes? HA and A minus are what we call a conjugate acid-base pair, okay? HA is the acid, A minus is HA's conjugate base. A minus, if A minus is the base, HA is its conjugate acid. So a conjugate acid-base pair is a pair of chemical species that differ by one hydrogen. Either the hydrogen is on or it is off. So when we had our H2SO4, the conjugate base of H2SO4 is HSO4 minus, okay? And the conjugate acid of HSO4 minus is H2SO4. Now, the thing is that you can be a conjugate base of something because you just take off the proton, okay? Anytime you want to find a conjugate base, you just take off a proton. But you might be too weak to take that proton back. And if you're too weak to accept a proton, are you able to act as a base? No. So these guys are conjugate bases of strong acids, but they are unable to act as bases. And that's because all of these arrows are all one-way arrows. So the conjugate bases of strong acids are unable to accept protons. So that means that HSO4, although it can act as an acid, it is unable to act as a base. Therefore, it is not amphiprotic. It is the one and only thing that has an H and a negative and is not amphiprotic. Is good? Okay. Any questions? Yes.
They sound double. Why can't they accept it?
Why can't they accept it? Because thermodynamically, it's totally unfavored. Entropy and enthalpy say no. They say it's HSO4 dissociates completely. It will not go back. Like if you have a weak acid, it sits here most of the time, and every once in a while it'll dissociate, and while it dissociates, another of its little mates will come back together, right? But most of the time it is together, right? But if you have a strong acid, it's like every particle that enters the water goes bam, bam, and they won't go back together. So they will not accept protons. Yes?
So for the basis, with the bottom, for example, H2O and IO3,
yeah, so all of these guys here, HIO3 and IO3 minus, that is a conjugate acid-base pair. Okay? So everything on the left-hand side is the conjugate acid of the thing on the right-hand side. Everything on the right-hand side is the conjugate base of the thing on the left-hand side. So these two are a conjugate acid-base pair.
So all the conjugate species differ by H?
Differ by a single H. Yes. We'll write that down at some point, but not on here because this is already too messy. Okay, so those are a conjugate acid-base pair, as are all of the other ones. Okay, so everything all the way down to the bottom. Now, when we get down to the bottom, you'll notice we've got equilibrium arrows all in the middle. Yes, all that middle part of the table, all equilibrium arrows. But when we get to the bottom here, what do you notice about the arrows now? Only the reverse reaction takes place. So really, sometimes I'll get people, and there'll be a multiple choice question. It'll say, is NH3 a strong acid, a strong base, a weak acid, a weak base? And I'll get people saying, oh, it's a weak acid because here it is. It's on the acid side and it's really low down, so it's a weak base. A weak acid. However, is NH3 able to act as an acid? If it were able to act as an acid, it would be able to donate a proton. It would be able to give away a proton. Is it able to give away a proton? No. These two guys here are unable to donate protons. And that's because we have these one-way arrows. Really, the OH minus and the NH3 are only there because we are actually really interested in the O2 minus and the NH2. Okay, the O2 minus, what kind of a species is an O2 minus? Acid or base? It is a base. Is it a strong base or a weak base? It is a strong base. Okay, and NH2 is a strong base. And you remember when I mentioned that multiple choice question where it's like, is NH3 a strong acid, strong base, weak acid, weak base? The other thing people will say is they'll look at NH3 and they'll be like, it's down in the strong base area. Therefore, NH3 is a strong base. Is NH3 a strong base? No, it's NH2 that is the strong base. Okay, so just watch out for that. It's one of those things where if your brain has a little moment, it might go awry. Yes?
So let's say hydrochloric acid, would that be amphiprotic?
Hydrochloric acid, HCl.
Hydrochloric.
Hydrofluoric.
Can you see that?
Can it?
Yeah, it's a way it's
It can give away an H. Can it accept an H and become H2F plus?
always.
Does that make sense? So what will happen is HF cannot be amphiprotic because it does not have a negative charge. The only thing without a negative charge that can accept protons is who? H2O, water, okay? And you'll notice that HF only appears on the acid side. You won't find it anywhere on the base side. Your amphiprotic substances will show up on both sides. So you'll see we have, for example, let's get rid of this and this. We have H2PO4 minus. It's got that H and it's got a minus, right? We can go down further on the periodic table and we should expect to see it on the left-hand side as well somewhere. H2PO4 minus. Okay, so here it is donating a proton. Here it is accepting a proton. Okay. We have, actually, let's see. Can you guys find who, as we go down our list, who is the first amphiprotic substance that we come to other than water? H2SO3 is one of them. Yep. Okay, so we have H2SO3. Or, sorry, H2SO3? HSO3. HSO3, it can accept a proton, and if we go to it further down the list, it can, where did it go? It's further down. Donate a proton. We missed one, I think. H212, huh? We got this one. It's H2C6H5O7 minus. And if we go down, we've got H2C6H5O7 minus. We also have HC2O4 minus. And if we go down further, HC2O4 minus. Yeah? Yeah.
Mentioned earlier, people were saying ammonia and H3 for a strong base.
Yeah.
But it is a base, right? It's not.
It is a base, but it is a weak base. Anything that is not in the gray zone is going to be weak. Okay, so it's in that middle area. So all of the things in the middle area are weak acids. So everything from here all the way down to here are all weak acids. Okay, everything from here all the way down to here are your weak bases. Okay, those are all weak. And then you got your 2 strong bases at the bottom on the right-hand side, and you have your 6 strong acids on the top on the left-hand side. All right. So if I gave you this list, let's give you a list. Which of the following are amphiprotic? Whoops. Se2 minus, HSE minus, H2Se, H3PO4, HPO4, 2 minus, and HSO3 minus. You may have done this for homework already, but if you haven't, there it is. Which of the following are amphiprotic? You don't even need the table for that. Okay. Se2 minus. Amphiprotic or no? No, why not? There is no H plus. You need to have an H plus. HSE minus, yes or no? Yes, we have both the H and the negative. H2Se, yes or no? No, because we have the H, but we don't have a negative. H3PO4. We've got an H, but again, there is no negative. HPO4 2 minus? Yes. HSO3 minus? Yes. How about HSO4 minus? No, why not? Its conjugate acid is strong. So even though it's got the H and the minus, no, because its conjugate acid is strong. There's no others like that because H2SO4 is the only diprotic strong acid. Okay, so there we go. All right. Let us then go to 4.1F, which is on page 42. You guys are going to do 4.1B, C, D, or sorry, C, D, and E. You've already done A and B with Mr. Colger. They will sort of review things that we're doing. We're putting it all together before you've seen the original bit. This is page 42. We are going to have a quiz on section 4.1 next Thursday. Okay. All right. So if a chemical is acting as an acid, it must lose a proton. Either it's going to lose the proton to water, or it's going to lose it to something else, and that something else would be some other base. When the acid loses its proton, it turns into a chemical species called, oh, there should be an S at the end of this, it's conjugate base. Fix that. So what I'm going to have you guys do is I'm going to have you write the conjugate base for this Bronsted-Lowry acid, this Bronsted-Lowry acid, and this Bronsted-Lowry acid. Once you've done that, you're going to take these 4 Bronsted bases and write their conjugate acids. Once you have done that, you're going to check with your partners and you're going to check with the people around you, because I'm going to use the cards to have people give me the answers. Okay? So go ahead, try those. Give me a little wave when you're finished. Anyone need more time? No. Okay. Stephen, who is the conjugate base of HCl? Cl minus. What did you do? Yeah, you take away an H plus, so it becomes, so you lose a positive, so it becomes negative, right? So we subtract an H plus, it becomes negative, and the H is gone. All right, HSO4 minus, its conjugate base is, Dylan? SO4 2 minus, yes. And HPO4 2 minus, conjugate base, Aditya, is PO4 3 minus. Excellent. Okay. And now we will move on to the conjugate acids. Who is the conjugate acid of CO3 2 minus? Ansel? HCO3 minus, yes indeed. So all we're doing is we are adding an H and a plus. So it becomes, we go from 2 negative to 1 negative. All right, CH3COO minus, its conjugate acid, John. CH3COOH. And hopefully most of you remembered that, of course, that acidic hydrogen goes on the COO group. If you didn't remember that, it does say over here, in organic acids, the detachable proton goes on the carboxylate group. What is the carboxylate group? That is the COO group. Okay, and when that hydrogen goes on, it stops being a carboxylate group and becomes a carboxylic acid group. Do you need to really know these terms? No, not particularly. AP does not get too excited about organic chemistry at all. If they do say something about it, they will give you all the information that you need. Okay? But good to know. All right, HPO4 2 minus. Its conjugate acid is Edward. HPO4 2 minus. Is it H3PO4 or is it H2PO4? Which one? That one is better because they only differ by 1 hydrogen. Okay. HCO3 minus. What is its conjugate acid? David. H2CO3. So let's make sure that we have defined a conjugate acid-base pair. Let's toss that at the bottom of the page. A conjugate acid-base pair conjugate acid-base pair, how many chemicals? 2, because we're dealing with a pair, right? So 2 chemical, and what do we call chemical things? Species. 2 chemical species that differ by a single H plus, or a proton. You should be able to define that. I think most of the rest of this page is stuff we've talked about already, and that recognizing amphiprotic substances, they must have a hydrogen, they must have negative charge. The exception is water, which is amphiprotic, and also the other exception is who? HSO4 is not amphiprotic. Okay, and I think everything else on this page was done already in the above. In these examples here, these 7 examples that we have, who are the amphiprotic substances? HPO4, because you can see here it is, and it is listed as an acid, but it is also here where it is listed as a base. So we have HPO4 2 minus. Yeah. And we also have HCO3 minus. HCO3 minus shows up here where it is a base, but it also shows up here where it is an acid. Are there any other substances in there that are amphiprotic, but maybe their amphiprotic partner is not shown? Any other amphiprotic substances in there? If you think you've got it, just give me a thumbs up. Okay. I'm going to draw a card for this one. So if you don't know, ask someone next to you. And if they don't know, go walk around until you find someone who knows. We good to go? Oh, Baran. H2PO4, yeah. We haven't written it anywhere else, but yeah, it is also amphiprotic. Okay. Chemicals that can act as either an acid or a base are called, everyone practice writing it so you know you can spell it. They are called amphiprotic. not ambiprotic. Sometimes I get people with like ambidextrous, but it's amphi. Another definition of amphiprotic, a substance that can act as both a what donor and a what acceptor. Proton. Proton, proton. Excellent. And that's it for this page. Again, we have done a lot of this already, but you can see we have the various acids here. We have the strong acids are this section here, whereas the other side, those are substances which, although they are on the base side, they are too weak to act as bases. So I-, not able to be a base. Okay, all the ones over there. At the top of the table, on the left-hand side, actually, you'll see we have all of the weak acids here. In this section, these are all our weak acids. We have all of our weak bases on the right-hand side in the middle. But if we look at the side of the table, it gives us the strength of the acid gets stronger as you go up or down. Acids become stronger as you go up the table. So we have our stronger weak acids at the top and our weaker weak acids at the bottom. But our stronger weak bases are at the bottom, and our weaker weak bases are at the top. What can you say about the Ka values of the stronger weak acids compared to the weaker weak acids? What can you say about the Ka values? Stronger weak acids have larger Ka values and weaker weak acids have smaller Ka values. Okay, so the larger the Ka, the stronger the weak acid. But also, if the acid is stronger, its conjugate base will be weaker. And if you have a stronger base, its conjugate acid will be weaker. Okay? So the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. And actually, I'm going to show you a little something that mathematically proves that. And do you guys remember what Kw is?
Water.
It is the K for water. And the water reaction, we actually have it shown down at the, why are you not erasing? There we go. We have it shown at the bottom of the table right here. H2O gives H plus plus OH minus. So what would the expression, the Ka expression for that be? Yeah, the value for that is 1.0 times 10 to the negative 14. What would the expression be? Yes. I'm going to put H first because everyone always puts H first, but you could just as easily put H second, okay? So we have H plus and we have OH minus. Why was I going through that? Right. But before we do that, I'm going to point out that who is the weakest weak acid on this chart? Water. Who is the weakest weak base on this chart? Water. Okay? So who is the strongest weak acid? Water's conjugate acid. Who is the strongest weak base? Water's conjugate base. Okay? And it's really funny because if we had a different solvent, like if we dissolved everything in ammonia instead of water, ammonia would be the weakest weak acid and it would be the weakest weak base. And so its conjugate acid would be the strongest weak acid and its conjugate base would be the strongest weak base. We'll talk more about that later. But anyway, so we were going to talk about why the stronger the acid, the weaker its conjugate base. It turns out that this table only gives us Ka values. So those relate, of course, to the acids. Do you imagine, though, that the bases probably have a similar value? What do you think those are called? They're called Kb. We won't actually deal with Kb formally until Unit 5. But the stronger the base, the larger its Kb. And it turns out that if you take Ka and you multiply by Kb, you get Kw. And because Kw is a constant, and these are for a conjugate acid-base pair. Okay, so you would have the one with the H. This would be HA, and this would be the Kb of A minus. So if HA is bigger, if the Ka is bigger, then Kb will have to be smaller. If Kb is bigger, then Ka will have to be smaller. Okay, but like I said, we're not actually dealing with Kb until Unit 5, so that's just a little preview. Okay? All right. We've already talked about our strong acids. We've already talked about our strong bases. We've talked about, is HSO4 minus amphiprotic? No. Which of these two equations is not possible? Equation 1 or equation 2? Which of these is not possible? Equation 1 or equation 2? Equation 2. The forward reaction will not proceed. Okay. La 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 la. In order for a chemical to act as an acid, it must be mixed with a base. So let's say we had an acid and it was like HCl, and then we threw that into some propane, some liquid propane, C3H8. C3H8 is not a base. It is unable to accept protons, so the HCl would not donate protons, so it would not act as an acid. It would just sit there. If it would even dissolve, because it is polar and the other one is non-polar. But anyway, let's just get rid of that. So if you have an acid, it has to have a base. Now, if we have HCO3, what type of a substance is HCO3? Is it an acid, is it a base, or is it something else? It is amphiprotic. However, if what it is mixed with is PO43 minus, what will it act as? It will act as an acid because it is with a base. So therefore, this one will act as the acid. Could you please predict the products of that reaction? What would we get? What's the first product we're going to get? CO3, 2 minus. And the second product we're going to get is going to be HPO4, 3 minus. Thank you. 2 minus. I got carried away. 2 minus. There we go. Who are the acid and the base in the reverse reaction? HPO4 2 minus is the acid, and CO3 2 minus is the base. What are the two? Why is there an E on the end of that? What are the two conjugate acid-base pairs in this reaction? I'm almost out of cards, so I'm going to shuffle. Have a chat with your neighbor, and I'll call somebody. Who are the conjugate acid-base pairs? I'll ask one person for one of the pairs, and I'll ask another person for the other pair. Everyone ready? Say no if you're not. You don't want to answer? Oh, you know one. Okay. What are the two conjugate acid-base pairs in this reaction? And if you don't know, go find someone who does. Are we ready? As ready as we're going to be, no one's saying no. Okay. Stephen, give me one conjugate acid-base pair. CO3 2 minus. Yes, we have two species that differ by 1 hydrogen. Okay, and the conjugate acid-base pairs will be on opposite sides of the reaction because the acid will react and turn into its conjugate base, and the conjugate base will react and turn into its conjugate acid. Who is the other pair? She's not here. Not here. Victoria. PO4 3 minus and H3PO4. Yes. Or sorry, not HPO4. 2 minus. There we go. Okay. I think we can skip the rest of that because we've already answered it. Now, the next thing we're going to do is we are going to predict which side of an acid-base reaction is favored. Okay, so do we have more product or do we have more reactant when the system is at equilibrium? So let's say we take a weak acid, right? This is a weak acid. And we mix it with a weak base. Who will be our products? HF and CN minus. Okay? In the reverse reaction, who is the acid and who is the base? HF is the weak acid, and CN minus is the weak base. Okay. So, how do we predict whether the products or the reactants are favored? Where do you think you might look that might help you figure out? You might look at KEQ. Yes, absolutely, you can do KEQ. But before we go there, we're going to do it just qualitatively without using numbers. States, everything's aqueous. You're going to look at your data booklet. What might you find in your data booklet that would help you figure out which side has the most chemicals there? Which side is favored? You would look at the Kas. Now, who would we be finding the Kas for? HCN and F? And HF, yes. So we're going to look at the Ka for HCN, and we're going to look at the Ka for HF. And I've actually done that down here somewhere. But let's also look on the data booklet, because on the data booklet, you can see that we have HF is here, and HCN is further down. So even without knowing the Ka values, you know that HF, is it stronger or weaker than HCN? You know that it is stronger, okay? So you can look at the values, but you can also just look at the position on the table. Come on. Why you not go back? Come on. There we go. So what we know is that HF has a value, Ka of 3.5 times 10 to the minus 4. That is bigger than HCN's Ka, and therefore HF is the stronger acid. It is also higher on the chart, so you can just see. You don't even have to look at the numbers. It's not a strong acid, but it is a stronger weak acid. What does it mean to be a stronger acid? What is it good at doing? Giving protons. In which direction is HF giving protons? Forward or reverse? Reverse. HF is better at giving protons. So where is this going to end up? Is it going to end up with more HF, or is it going to end up with more F minus? We're going to end up with more F minus. So basically, you just look at your two acids. You say, this one is stronger. This one is the weaker acid. This one is the stronger acid. Which side do you end up with more of? You end up with more of the weaker stuff. There's a few ways of thinking about it. You can think about it this way, you know, where the HF is better at giving away the H+, so you end up on the side with more F-. I always like to think of it kind of like, if I'm HF and I'm stronger than the acid that's over there, which direction is this reaction going to get pushed? If this push is stronger than this push, which direction will it go? Plain hand is stronger than glove hand. Which way will it go? Left. So that's going to end up on the reactant side, yes? So this will be your stronger acid. As it turns out, this will also be your stronger base. And this will be your weaker base. Whichever side has the weaker acid and base will always be favored, because the strong ones are good at pushing away from themselves. Yeah? And if none of that makes sense to you, well, they do say that the weak inherit the earth. Actually, it's the meek. So you end up with more of them? I don't know. Maybe it'll help you remember. I don't know. The weak side is always favored. Okay? All right. A stronger acid is better at giving away its protons. Since the stronger acid HF gives its protons away in the reverse reaction, that means that the reverse reaction is favored, and therefore you are going to end up with more reactants. So the reactants are favored. Will the KEQ of this equilibrium be large or small? It's going to be small because we have the reactants are favored. The denominator will be big or small? Big. And the numerator will be small. And if our numerator is small and the denominator is big, we end up with a small number. So KEQ will be less than 1. How are we doing with that? That's okay? All right, we're going to do one more that's even more complicated, and then we're done for the day. Yeah, we have time. What is more confusing about this one? Here's on our next page, we have our 2 reactants. What do we know about these 2 reactants? What's that? Okay. Take a look, chat with your neighbor. What is special about these 2 reactants? They are both amphiprotic. They both have hydrogens. They both have negatives. If you have 2 amphiprotic substances, how do you decide which one donates protons and which one accepts protons? Whichever one is the stronger. Okay, so whichever one is the stronger, acid will accept. So I would just look at the Ka values, or you could look at the Kb values, but they aren't given to you on the table. So let's go look at our Ka values. And in fact, I don't need to because I've written them down here. H2C6H5O7 has a Ka of 10 to the negative 5. Ka of HSO3 has a Ka of 10 to the negative 7. So who is the stronger acid? H2 blah, blah, blah. C6, H5, O7, negative. That's the stronger acid, and it will act as the proton donor. So we're going to have a hydrogen move from here to there. And what will our products then be? HC6, H5, O7, 2 minus, and H2SO4. Now, in our forward, let's label all of these species as whether they are acting as acids or bases. So the H2C678, this is acting as an acid. HSO3 is acting as a base. How about in the reverse reactant? That should be a 3 there. Who is acting as the acid in the reverse reaction? H2SO3, that is our acid. And who is acting as the base? The other guy. I don't even know why I asked that because it's the only thing left. Who is going to be favored, and how do you know? You're going to look and you're going to say, I have 2 acids. So when you have 2 amphiprotic substances, first of all, you have to say, of those 2 amphiprotic substances, which one is stronger, so you know who acts as the acid and the base. Then you have to say, who's the acid in the reactants, who's the acid in the products, and say which one of those ones is the stronger acid. And we have the Ka of H2SO4 is bigger than the Ka of H2C6H5O7. So that means that this guy is stronger and this one is weaker. So who is going to be the stronger base? Remember, the weaker the acid, the stronger its conjugate base. So the 2 strong things will always end up on the same side. The 2 weak things will always end up on the same side. So who is favored? Reactants or products? Reactants are favored, and that's because H2SO3 is better at giving away protons, so it becomes HSO3, so you end up with more HSO3. HC6H5O7 2 minus is better at grabbing protons, so it will turn into its conjugate acid more, so you will end up with more of that, so you end up with more reactants, so the reactants are favored. So the reverse reaction is favored, and therefore the reactants are favored. Will the KEQ be large or small? KEQ will be small, less than 1. Do you guys want to try one more? We have 5 minutes. It's up to you. I don't care. I ran out of time. I didn't have any other time with the other class. So I just gave them the homework. Would you like me to just give you the homework? Okay, so your homework is 4.1 C, 4.1 D, and 4.1 E. Those are really just watch the videos. Probably it will be a little bit of review, so you can put it on like 1.5 times or 1.75 or whatever and zoom through them. Also, the exercises on pages 48 and 49. Is good? Okay. Oh. Do I have to teach grade 9s after this? They're actually lovely people. They're really, really lovely. I'm just hoping they're as exhausted as I am. because I got no energy today.